Voltage regulators are very important components and they are integral part of a professional and stable circuit design. You, as a circuit designer, must be careful of selecting right voltage regulator. If not, your project will not work fine and it may face many problems. Selecting best voltage regulator for a particular application is a challenging task and actually it is very important. Most of newbies are not aware of the importance of selecting right voltage regulator, and in most of their designs they use regulators that are already familiar with. In this video, I'm going to discuss 13 important and different parameters of voltage regulators, and also I will introduce more than 5 voltage regulator part numbers and their specifications to help you use them in your projects with maximum confidence. After watching this video, your perspective about voltage regulators will definitely change. Stick around for the full experience. Hey everybody, this is Electronic Wizard at your service. Let's begin with DC voltage regulator definition. A voltage regulator is an electronical component that regulates voltage. I believe this is not a good definition. It is better to say that a voltage regulator is a component that takes a variable or unstable or noisy input voltage and converts it to a steady, clean, predefined, precise, fixed, and strong output voltage. This guy is most famous regulator in my world. When I was a child, I thought there was only this guy, this regulator, L7805. Even though it did overheat easily and screw my projects up in most cases, it was present in almost all of my projects. To be honest, my progress in electronics accelerated from the time I began using various voltage regulators. It is very important to know different voltage regulators and their specifications. This block presents a voltage regulator. It gets an input voltage here and it provides an output voltage here. The output voltage has to be fixed regardless of fluctuations and the voltage level at input. For example, if the input voltage fluctuates between the range of 9 volts to 12 volts, a 5 volt regulator like this L7805 must maintain a steady 5 volts at output. You may ask, should the input voltage necessarily be higher than the output voltage? Great question. Let me introduce the first parameter to consider. Attribute number 1, buck or boost regulators. Voltage regulators fall into two major categories: buck regulators and boost regulators. Buck regulators are able to regulate a higher voltage to lower voltages. I mean, stepping down the voltage, like this L7805, which is able to convert high voltages like 9 volts or 10 volts or even 12 volts to 5 volts. In contrast, boost regulators are able to regulate low voltages to high voltages. I mean, stepping up the voltage, like this XL6009, which is a boost regulator, and it is able to convert low voltages like 10 volts or 6 volts or even 4 volts to high voltages up to 40 volts. However, most of the regulators in the market are buck regulators. This is the simplest circuit you can use to get a linear regulator like this L7805 up and running. I'm going to build this circuit and we will test it together to see how it works. You can see here that the output voltage is 5 volts. No matter how much I change the input voltage, the output voltage stays fixed at 5 volts. This is the datasheet for a boost regulator, as you can see here. It is written here. Right here on this page, you will find the simplest startup circuit for this regulator. If you build this circuit precisely, the regulator will start working and can convert lower voltages into high voltages. Building that circuit might be a little tough, which is why I want to test it using this module. This module has that exact circuit already built into it, so it's ready to test. When I change the input voltage, the output voltage stays constant at 30 volts. No matter how much I change the input voltage, I'll still get 30 volts on output. Note that this module converts a low voltage to high voltage. For example, right now it's converting 5 volts to 30 volts. Being a boost or buck regulator is one of the most fundamental characteristics of a voltage regulator, right? Anyway, let's move on to the next attribute. Attribute number 2, switching or linear regulators. Any voltage regulator will fall into one of these two categories, switching or linear. This attribute indicates the mechanism of operation that regulator employs to keep the output voltage constantly equal to the desired voltage. This is the mechanism of operation of a switching regulator. Its mechanism is very simple. There is a switch here, mostly a MOSFET or other type of electronical switches, and a capacitor at the output. When the regulator is started, this capacitor is empty and the voltage at the output is 0 volts. The regulator has a control circuit to open and close the switch periodically and automatically to keep the voltage at the output close to the desired voltage. For example, if the input voltage is 10 volts and the desired voltage at the output is 5 volts, the regulator closes the switch until the voltage at the output reaches 5 volts and then opens the switch. After that, it will check the output voltage periodically, say 1000 times per second, and if the voltage at the output is under the desired value, it will close the switch again to help the output voltage reach again the desired value. Suppose that a load is placed here at the output. The load will consume the energy stored in the capacitor and it will cause the voltage of the capacitor to decrease here, here, or here. Then the regulator will charge the capacitor again until it reaches again the desired value. So there should be some fluctuations at the output voltage similar to this diagram. I'm going to do a simple experiment to see this mechanism of operation and these fluctuations at the output voltage. This is an LM2596 switching regulator module. The IC itself is here. Look, this is LM2596 IC, which is a switching buck regulator. Look at its datasheet. It's here. Simple high efficiency step down buck regulator, and this is the most simple to make it running. Look, this is the most simple circuit to make this IC up and running. Note that this was XL6009, which was a boost regulator, but this is LM2596, which is a buck regulator. Look here, when I change the input voltage, the output voltage stays fixed, which was predictable and absolutely normal for this module. But the interesting point is in the output voltage. Here, I should be able to see those fluctuations in the oscilloscope. Look here, these tiny sawtooth-shaped pulses are generated by the switching mechanism. These tiny sawtooth pulses shows that the switch is closed for a tiny period of time. Actually, these pulses are very tiny and they're negligible. Look, the maximum amplitude of these pulses is around 25 millivolts. But what if I add some more load at output to draw more energy from the output and empty the capacitor faster? In that case, these pulses have to increase, right? I'm counting down the seconds until I test it. Now, if I add more load at the output, we can see that these tiny sawtooth-shaped pulses will grow, and if I add even more and more load at the output, they will grow even more. Look. Now you can see that the amplitude of those tiny sawtooth-shaped pulses are increased. By the way, any switching regulator has an attribute related to the frequency of opening and closing the switch. We can find it by measuring the frequency of these pulses. We have learned about the mechanism of operation of a switching regulator so far. Now is the time to see how a linear regulator works. This is simplified diagram of a linear regulator. We have a variable and controllable power resistor here. In most cases, a MOSFET or something is used here to simulate a variable resistor. Also, there is a control unit here to control the resistance of the drain source of the MOSFET by adjusting the voltage of its gate. I'll give you a numerical example. There is a constant and high value resistor here at the output, say 1 mega ohm for example. Suppose that there is no load at the output, so the control unit will adjust the resistance of this resistor to 1 mega ohm and this will produce 5 volts at the output. Look, there are two resistors with the same resistance and this will halve this 10 volts and generate 5 volts at output. Now suppose that a 20 ohm resistor is placed at the output as load. In this case, the control unit will reduce the variable resistor to 20 ohms by applying proper voltage to its gate terminal. So we will have 40 ohms in path in total and 250 milliamperes will flow through these resistors. The power dissipated at the load here is not our business, but the power dissipated here is. In this case, the regulator will dissipate 1.25 watts to deliver 250 milliamperes to the load. Now, suppose that the load is 5 ohms instead of 20 ohms. In this case, the total resistance in path is 5 ohms plus 5 ohms equal to 10 ohms. So the current passing through these resistors is 1 amperes and the regulator will dissipate 5 watts. In this case, using a heatsink is definitely necessary. This is why linear regulators dissipate more power and get hot easily. On the other hand, the mechanism of operation of linear regulators do not allow them to boost voltages, so all of boost regulators are switching regulators. Anyway, the next attribute is attribute number 3, efficiency. Efficiency is the percentage of the input power that the regulator converts to usable output power. It is obvious that a higher efficiency is better, right? Especially for a battery-powered application. Linear regulators are not much efficient because of the power dissipated here at this resistor simulator, especially when the input voltage is much higher than the output voltage. Look, the power dissipated here is calculated by multiplying the current drawn by the load and the voltage dropped across this resistor. The higher the input voltage, the higher the voltage dropped across this resistor, and consequently, the higher the power dissipated on this resistor inside the regulator. For example, if the input voltage is 12 volts and the output voltage is 5 volts, this resistor should drop 7 volts here to make the output 5 volts, right? So, by drawing 1 ampere by the load, dissipated power on this resistor will be 7 volts, the dropped voltage across this resistor, multiplied by the current drawn by the load, which is 1 ampere. So it has to dissipate 7 watts here. But if the input voltage is 8 volts, this resistor has to drop 3 volts. Now, if the load draws 1 ampere, this resistor will dissipate 3 watts. This is why linear regulators operate cooler when the input voltage is low, close to output voltage. It was an interesting point, right? It definitely worth liking the video, right? Thank you. Anyway, here you may ask, if decreasing the input voltage makes regulator more efficient, can we bring the input voltage as close as possible to the output voltage? This question will lead us to the next attribute, attribute number 4, dropout voltage. Dropout voltage is the minimum difference between the input and output voltages needed for the regulator to function properly. A lower dropout voltage is better for situations where the input voltage itself is low. This is datasheet for L7800 linear regulator series. Look at this table in page 7. The dropout voltage for this device in this condition is typically 2 volts, and at the worst case scenario it is 2.5 volts. This attribute indicates that we have to apply input voltages at least 2.5 volts higher than the desired output voltage to guarantee proper function of the device. For example, if you are using L7805 to create 5 volts, you have to apply 7.5 volts or more to the input terminal to make sure that the device will work as it should. There is another attribute that indicates the maximum input voltage. Attribute number 5, input voltage. Input voltage indicates the maximum voltage that the regulator can safely accept on its input side. You will need a regulator that can handle the voltage coming from your power source. If you look at the table 1 here in page 5, the datasheet indicates that for L7800 family, if the output voltage is from 5 volts to 18 volts, the input voltage has to be less than 35 volts, and for the output voltages equal to 20 volts or 24 volts, the input voltage has to be less than 40 volts. For any regulator, you can find this parameter in its datasheet. Now, we are going to shift our focus on the next attribute. Attribute number 6, output voltage. Output voltage of a regulator can be fixed or adjustable. For example, L78XX series are fixed output regulators, meaning that the IC is designed to create a fixed voltage at output, say 5 volts or 9 volts. But some other regulators like LM317 are adjustable. An adjustable voltage regulator can make desired voltages using 2 adjusting resistors. Look, this is datasheet for LM317, a popular linear adjustable voltage regulator, and this is the most basic circuit diagram of this IC. There are 2 adjusting resistors here. This one, which has to be fixed and equal to 240, and this one, which is the adjusting resistor. By changing the value of this resistor here, you can change the output voltage. Also, you can use a potentiometer instead of this adjusting resistor to make adjusting the output voltage easier. Also, you can use this formula to calculate the output voltage. These are modules we have already seen in this video. Look, there are potentiometers on them to adjust the output voltage. Look here, this one and these. For example, on this module, you can adjust the output voltage using this multi-turn potentiometer. See, when I turn the multi-turn potentiometer, the output voltage changes. Even though most of regulator families are exclusively fixed or adjustable outputs, there are some regulator families that have both types. For example, MIC29 series are linear regulators that have both fixed and adjustable outputs. Another example is LM2596 series that are switching regulators and have both variations. Anyway, let's move on to the next attribute that the output of a regulator has. Attribute number 7, output current. Output current is the amount of current that the regulator can safely provide. Look here, L7800 family can provide up to 1.5 amperes. LM317 can provide up to 1.5 amperes. LM2596 can provide up to 3 amperes, and MIC series can provide up to 7.5 amperes. Some voltage regulators have very low output current, like this LM336, which is a 2.5 volt voltage regulator, which is able to provide only 10 milliamperes of current at output. Actually, these ICs are used for making reference voltages, and because of that, in most cases, they are called reference voltage ICs. Anyway, our next topic of discussion is attribute number 8, polarity of the regulator. Regulators can be negative or positive. For example, L7805 is a positive voltage regulator, but it has a negative twin, L7905. This is what all we are familiar with. A positive voltage regulator which takes a positive high voltage and makes a positive low voltage. For example, this L7805 regulator takes positive 12 volts at input and makes positive 5 volts at output. But a negative voltage regulator takes a lower negative voltage and makes a higher negative voltage. For example, this L7905 negative regulator takes minus 12 volts at input and makes minus 5 volts at output. By the way, since these voltages are negative, I said that this minus 5 volts is higher than minus 12 volts. Essential attributes of voltage regulators has been discussed in this video so far, but there are some additional attributes or parameters that I will only introduce briefly. Attribute number 9, package type. Different voltage regulator ICs come in various physical packages. Some are small and surface mount, while others have larger through-hole pins for easier soldering. Consider the available space on your circuit board and your soldering skills while choosing a package type. Attribute number 10, cost. Voltage regulator ICs can range in price depending on their features and capabilities. If you are building a simple circuit, a basic regulator like L78XX series might be sufficient. But for more complex application, you might need a higher performance and potentially more expensive option. Attribute number 11, availability. Make sure the voltage regulator you choose is readily available from a reputable supplier. This can be important if you need to replace a part in the future. Attribute number 12, ease of use. If you are a beginner, you might prefer a voltage regulator IC with a simpler datasheet and easy to understand specifications. This is a wise decision for beginners to work with easy to use regulators in their projects. By the way, some regulator ICs needs plenty of external components which makes using them difficult, while others need a few external components, mostly an input and output capacitor only. Attribute number 13, protection. Last but not the least attribute is protection mechanism. Some voltage regulator ICs include built-in mechanisms for protecting the regulator itself from excessive heat, overvoltage, overcurrent, or short circuits. The more these mechanisms, probably the more suitable the regulator to use and the more expensive. You can consider all these attributes and select right voltage regulator for your circuit. Anyway, we have reached the final moments of this video. Thanks for watching. If you want to see more amazing content like this, make sure to like this video and subscribe to my channel for updates. Until the next video, take care of yourself and have a good one. See you in the next video.